Welcome to the Physics Odyssey channel. I'm Vinny Physics. Today we're going to be talking about roller coaster physics using NoLimits2 roller coaster design and simulation software. This is actually a roller coaster built with NoLimits2, so most anything is possible. Now we'll talk about each one of these types of turns and why they give you the effects that they do, a little bit about the mathematics behind various turns. In this lesson, I am going to present motion using NoLimits2 roller coaster simulator. And in this video, I'll cover things like accelerated motion along a straight line, curvilinear coordinate system, computing vertical and tangential acceleration along various points of the roller coaster, including these three sections. And then video 2, I'll get into zero G curves, negative G curves, horizontal and lateral Gs, circular loops versus teardrop loops. In video 3, we'll talk about a roller coaster I designed and why it is so dangerous using the physics you'll learn in these videos. Hit the subscribe button if you want me to send you notifications on up and coming videos. To fellow teachers, if you are interested in learning more about using NoLimits2 to teach motion, email me. My email address is funbeffphy@gmail.com. If you want to use NoLimits2, you can purchase it. Here's the link, NoLimitsCoaster.com, $39. I think it's worth it. It's been a blast using it. You can also download a demo version and try it out before you buy it. Okay, first thing I'm going to do is talk about coordinate systems. Normally, probably most of you are used to using a coordinate system which is fixed. It does not move. In modeling roller coasters, it makes sense to attach a coordinate system to the roller coaster. And such coordinate system will have three directions. 1, in the direction of travel. 2, normal to the direction of travel, which is 90 degrees to the direction of travel. And 3, binormal to the plane of the vectors above. And I'll talk a little bit more about that here in the next couple slides. Okay, so here are the 3 vectors we will use in modeling and analyzing roller coasters. It's actually really simple, so don't let this scare you. These 3 different vectors, and they're changing directions as the roller coaster is moving. This would be a side view of the roller coaster going along a curve. The acceleration vector in the direction of travel is called the tangential vector. Perpendicular to this vector, towards the seat of the car, is the vertical acceleration vector. And in this case, out of the page, in this direction, would be the horizontal acceleration vector. Now, if we're in a helicopter looking down at the roller coaster as it's moving, this would be the direction of the horizontal. This would be the direction of the tangential. If we're looking at the back of the car as it's going into a bank turn, this would be the horizontal, and this would be the vertical. So why do I choose to use the terms horizontal, vertical, and tangential when most engineering dynamics books are using tangential, normal, and binormal? Well, I think it's more intuitive for one, and also it's the directions that NoLimits2 uses and provides data as the coaster is moving through the tracks. Centrifugal versus centripetal. So when I'm going to talk about centrifugal acceleration as opposed to centripetal because I am most interested in knowing what the rider is feeling. The rider is feeling a centrifugal acceleration. Okay, next I'm going to introduce you to some topics you may already be aware of, but I think are important for you to understand roller coaster physics. The first is acceleration along an incline. So imagine some object is on an incline. And since we're doing roller coasters, imagine it's a roller coaster car on an incline. Okay, gravity exerts a force on this object. Now, gravity is directed towards the center of the Earth, okay? So let's say that's the center of the Earth. That's really where the gravitational vector points to. but it has components along the incline. One is perpendicular to the incline, and one is parallel to the incline. The perpendicular component of gravity is g, which is 9.8 meters per second squared, or 32 feet per second squared. We're going to use meters, so 9.8 meters per second squared, times the cosine of this angle. Okay? And you can use a little trig to prove that to yourself. The component of g parallel to the incline is g sine of this angle. So if you put an object on an incline, and let's assume it has no friction, it's going to move in this direction, slide in this direction, at g 9.8 times the sine of this angle, and it's going to effectively weigh 9.8 times the cosine of this angle. Centrifugal centripetal acceleration. So now imagine something is moving in a circle. A force will be exerted on the object towards the center of the circle, and the magnitude of such force is going to be its velocity squared divided by the radius of the circle. Centrifugal is the same magnitude, it's just the opposite direction. Now, the reality is it's pretty rare for a roller coaster to travel in a circle. More likely, it's going to be doing something like this. Right? But at this instant, it will be moving in a circle of this radius. And this radius is very important so that we can compute the centrifugal acceleration. So combining the two, we get the vertical acceleration of the roller coaster at various points. So it's the centrifugal plus the gravity, again, perpendicular to the incline. And since we're interested in the number of g's, which is how NoLimits2 reports it, we're going to divide that by g. So I'll be applying this equation over the next several videos. So at this point on an incline, there is no curve, so this would be 0. And this would be g cosine of 60. So the number of g's would just be cosine of 60. The tangential, again, if this thing were sliding, would be g sine of theta. Theta is, again, the banking angle, or the inclination angle. But roller coasters don't slide. Roller coasters roll. So g sine of this angle is not the appropriate equation to model acceleration due to gravity. This is the proper equation for something rolling. And this is not something I'm going to get into in this series of videos because I'm going to be focusing on vertical g's and horizontal g's. Okay, radius of curvature, I mentioned this previously, as a roller coaster is taking a turn, for some instant, it's going to be moving in a circle, and we imagine what that circle looks like, and find its radius, and that's the number that goes in here. Sorry. Plus g cosine theta over g. Those are vertical g's again. It's a really interesting function, a fascinating function, and it's this. So let's just say this is a roller coaster curve. And we plot the x and y values of this curve. All right, so we create some coordinate system, say at this point, compute the x and y values, and then fit a function to that. So now we have y as a function of x. If we apply this set of operations to that function, we can find the radius. Now, I don't have equations for these curves for the roller coasters. It goes through the tracks, so we're just going to estimate it. Okay, a good assignment for students at this point is to complete 3 tasks. One is to compute the vertical g's, or vertical acceleration, same thing, on an incline. One would be to compute such value at the recovery of a drop. And the third would be to compute the acceleration of the car due to braking. And I'm going to do each one of those. Okay, so I want to compute vertical g Vertical acceleration, same thing. For the car, at this location, along this incline of constant slope. Now the general equation for vertical acceleration is g cosine of this inclination angle, call it Greek symbol theta, plus v squared over r. Sometimes these point in the same directions, yeah, add them. Sometimes they point in opposite directions. And throughout this presentation, I'll demonstrate points along the track where they have opposite directions. In this case, gravity, remember gravity is always straight down, but it has a component perpendicular to this incline, and that's g cosine of this angle. It also has a component along the incline. It's g sine. Okay, what about centrifugal? Well, there's no curve here, so we don't have any centrifugal acceleration. So the only vertical acceleration we have here is g cosine of this angle. What is that angle? Well, using some trig you learned in high school, you can compute that. Tangent of this angle is equal to this length divided by this length. Now I've set these to 10-meter blocks. Okay, so y over x. The y is 30 meters. The x is 20 meters. Okay, the units cancel. So that's 1.5. So what angle, such that when you take the tangent of it, you get 1.5. Well, if you take the inverse tangent of both sides, you can plug this into your calculator, and your calculator will give you 56.31 degrees. Call it 56.3 degrees. Okay, so now if you plug that into this equation, you get g cosine of 56.3, and that is equal to 0.56 Gs. Okay, now you can verify that in No Limits by selecting the G-force cone up here, zooming in, and looking at that, and that says 0.57 right here. So No Limit says vertical G 0.57. I have 0.56. Okay, close enough. Difference is probably due to me not measuring precisely the x and y values, but very close. So there you have it. So what does that mean? So a person riding this roller coaster at this point, assuming they're sitting on a scale, the scale will only read 0.56 their normal weight. Okay, again, this is acceleration. Force, it's acceleration due to gravity, and in this case it's AV, because you're on an incline, and that's weight, and that's going to be equal to mass times 0.56 G. Okay, so there you have it. You weigh a little bit more than half your normal weight on this incline. So if you want to lose some weight, weigh yourself on an incline. Okay, so the next thing I want to show you is how to compute acceleration vertical recovery of a drop. So right here. Okay, we're going to use the same equation. Still G cosine inclination angle plus V squared over R. So what I need is the velocity here, because we have curvature here, so we're going to get centrifugal. Direction. G, right? G is always down. So they're going to sum. That's correct. We're going to sum those. Okay, this part is easy. There is no inclination angle point, so we just have G there. It's like weighing yourself on a flat surface. You just weigh your normal weight, 1G. Plus V squared over R. Okay, to determine the speed at that point, we can turn on the speed comb in NoLimits2 and put the cursor right there, and it'll tell us the speed. And the speed at that point, as you can see right here, is 87.2 kilometers per hour. Okay, I'm going to use just 87 kilometers per hour. So V, 87 kilometers per hour. If you multiply that by 0.28 meters per second per kilometers per hour, so we're going to convert it to meters per second, I get 24.4 meters per second. Okay, so why am I converting that to meters per second? Because G here is in meters per second squared. If G was in kilometers per hour, and we could convert to kilometers per hour, then I could use 87 kilometers per hour here. But standard units in physics is meters, seconds, and kilograms. So I went ahead and converted this to meters per second. So now I'm going to plug that into the equation. 24.4 divided by R. 24.4 squared. 24.4 squared divided by R. Okay. R is the radius of the circle at this point of interest. Now, this circle would be quite a bit different than this circle, right? So at every point on the curve, the radius is different. So if I were to draw a circle at this point, just kind of guessing here a little bit. I believe it would look something like that. Okay, so a radius of approximately 20 meters. Okay, and that's what we're going to plug in here. Okay, and I'm going to go ahead and put 9.8 for G. It's 9.8 meters per second squared. Now, NoLimits provides vertical acceleration. Again, they call it vertical G's in terms of the number of G's. So I'm going to divide that by 9.8, which is 1 G. Plug all the values in and put this into my calculator. I get vertical acceleration of 4.03, and that's in number of G's. And if I put my cursor here, first highlight this area here for G-force comb, and put my cursor here, NoLimits right here is giving me 3.96 vertical G's. Okay, so it's about the same. Now, I wouldn't expect my estimate to be exactly like NoLimits2 because I'm just approximating the radius of this curve. So what does that mean to somebody riding a roller coaster at this point? What does that feel like? Okay, if they're sitting on a scale, what will the scale read? Well, let's say you weigh, I don't know, 150 pounds. It's going to read 4 times that. So it's going to read 600 pounds. So the third scenario I want to show you is acceleration due to braking, or you might want to call it deceleration. The scenario here is the roller coaster goes up an incline, it comes down, has a very high velocity, and then the braking station kicks in here. The braking station will have a set deceleration of 2 G's. Okay, so if I know the velocity before the brakes are applied, and I know the deceleration rate is 2 G's, I should be able to figure out how far it takes to bring the thing to a stop. And I'm going to compute that mathematically and compare it to what the simulation shows. Now, I can tell what the simulation predicts by using the speed cone here and zooming in on the braking station. Okay, so there's the braking station, the white part, all right? There's where the braking station starts. You see where that little blue thing is? That's the start of the brake. I'm going to zoom in. Okay, that's the start of the braking station. So as you can see, the speed drops. And it brings it to a stop, and here's each one of these is 1 meter. So that's 10 meters, 18, 19, looks like about 19 and a half meters. This thing is at a stop. Okay, so let's run it. We'll take a look at it, and then we'll do some math and verify that it's about 19 and a half meters to bring the car to a stop. Okay, we can always hit F2 to see what the key stats are. This is telling us vertical G's, horizontal G's. You can also slow this thing down by hitting the plus and minus keys. Okay, so there we go. Okay, I'm going to slow this thing down to 0.25. I'm going to hit the pause key. Well, I want to know the velocity right before it starts to go into the braking station. Okay, there's the braking station right here. And let's see what the velocity is. So the velocity is about 98.7 kilometers per hour. So 98.7, okay. 98.7, and that's about 19.5 meters. All right, so let's do the math and see what we come up with. Okay, 98.6, 98.7. Convert that to meters per second. So multiply this by 0.28 meters per second per 1 kilometer per hour. And this is what I got, 27.6 meters per second. The acceleration rate is 2 G's. Now 1 G is 9.8 meters per second squared. It's going to be into the direction opposite of this. So it's minus, so that's 19.8 meters per second squared. That should be a squared right there. Now I'm going to plug it into this equation. This equation can be derived from Newton's second law of motion, F is equal to ma. In another video, I actually do that. So this is the equation I'm going to use. I'm going to plug in everything that's relevant to this problem. The final velocity is 0. The initial velocity is 27.6. We're going to square that. Minus 2 times 2, right? The equation is 2 times acceleration. Our acceleration is 2g. So 2 times 2 times 9.8x. Okay. And then do a little algebra on this. I'm going to subtract this from both sides. Divide both sides by 2 times 2 times 9.8, and I get 19.4 meters, and that's about what it came to a stop in the NoLimits2 simulator.